Today, it's my honor to introduce our new product called ReeWell. It's world's leading AI-driven intelligent scheduling platform. So today is a form of a webinar. So actually, if you have any questions, you can raise it at any time, and I will answer it. Okay, so all the solutions comes from the problems. So what's the problems are we facing now? Nowadays, a lot of traditional terminals trying to reform their traditional operation style. They are introducing more and more intelligent devices, such as the autonomous driving trucks, or some remote control QCs, RTGs, or ARMGs. So with more and more the intelligent devices are introduced, obviously we have a lot of misalignments in different level. I think the biggest problem would be the point one we listed, which is the data misalignment. Since we have a lot of different devices, they are intelligent, but the data from them actually create a data silos. That means every device has its own data, but they cannot share with each other. The problem is obviously is a barrier to try to orchestrate all the devices into the same plan. That means we cannot fully use of the data, although it is full of value. So that's the point one. Obviously, we have the data misalignment. And point two is we have the process misalignment. As we all know that from the normal terminal operation, we actually organized by different departments, such as the trucks will be arranged by one department, and RTGs for another one, and also the QCs. So different planners from different departments have a different plan for different devices. That can introduce the process misalignment in every step. We all know that for a single, for example, we have a loading process. We have to pick up a container from the yard. So firstly, we have to assign a car, assign a truck, which is to pick up the container. And of course, it should be empty. And then we should assign a task for it. That means where the container is, and then we have to assign a RTG or a RMG to pick up the container. So in this small picking up process, we actually have two devices and two planners for it. In the traditional operation, they have to communicate with each other, maybe through speakers, maybe they have shared a plan through some pad, or some a common commander. But actually, finally they are from different departments, so that cannot be aligned in the at the same time. That's what we call the process misalignment. And point three is obviously introduced by point one and point two. That means we have data misalignment, we have process misalignment, and which is the reason of the timing misalignment. Of course, if we have we cannot share, we cannot know the current situation of all the devices. We have the barrier on the planning stage. Uh, the result or the timestamp of every process would be misaligned. Uh, we still use this loading or picking up process as an example. We already signed a empty truck, and we trying to pick up a container from some specific yard. But when the truck arrived there, the RTG is not finished. That means it may have doing the previous task, or it's running to the destination but still not picking it up. So this misalignment occurs everywhere. Despite we have a lot of intelligent devices for its own process, but all the intelligent devices for now is not well organized. So, how do we solve that? How to organize all the intelligent devices? That's the purpose of how do we thinking of this question. So, if we would like to solve this problem, we should understanding this complexity of the pod scheduling. The problem has now been formed that we have to solve the problem that to organize all the intelligent devices from every process in the terminal operation. But how do we do that? As we all know that the more devices we're considering, the more complexity of the problem is. I'll give you an example as shown in the figure. If we have a single vehicle, we have tasks. The combination of all the task assignment would be the 5 factorial, which equals to 120. We have 120 possibilities for that. When it comes to a large scale, such as we have 10 trucks and 10 tasks, the solves or the solution of this problem would be the 10 factorial, which is a huge number. It's over 300 million. It's over 3 million. But when we step into a larger scale, which is to the entire port, such as we have 200 equipments, which could involve the AQCs, the RTGs, and all the trucks. They can all involve into the equipment's aspects. And since we have 200 tasks, the total combination of them is a really huge number, which is larger than the entire universe. So it actually exceeds the number of the atoms in the observed universe. How do we solve that? W- It obviously is a NP hard problem. So in order to solve this problem, we actually raise up a four-layer architecture to uh, uh, to consider this as a methodology of solving this problem. So this four-layer architecture, we call it a data, situation, decision, and execution architecture. And we name every level and consider every level as a single, as a independent product in our product metrics. So this could be a little bit abstract, but we can consider this problem as a control problem. That means this is a control system which involves the input, the model, the controller, and the output. So it can be mapping to the four levels of the architecture, where the input should be the L1 data collection, or what we call the Cactus. So in this level, we collect all the data from different devices, such as the status of a single vehicle, like the speed, the path, the battery or something. So and also we can collect all the data from some edge calculation nodes, such as the camera. We can collect all the videos from the camera to and to analyze these videos to consider what happens now. So that's the level one Cactus, which can be considered as the input to the control system, and it is responsible for the data collection. And for level two, we call it Hymala, which can be considered as the model of the world. And it is built for the world understanding, and it provides a sandbox to simulate all the data. So in this level, we actually received all the data from L1 Cactus, and we began to build or to recover what happens now. For example, we have all the positions of the vehicle. We have the vehicle from the we have the videos from the camera. We know the traffic congestion now, and we know the single vehicle's speed or something, so that we can consider whether we need to speed up or slow down, or we need this vehicle to detour or pick up the shortest path. So Hymala actually provide the understanding of the word of the situation now. So it's a part of the situation awareness. And at the same time, since it is a model of the world, we actually build up a sandbox, try to simulate what is going on in the next hours. That means we provide the current situation to the model. It can provide the prediction of the next minutes, next hours for the current operation. So in level two, Hymala model, we actually provide this function. So in level three, we actually have the data. We already have the model. Then we need to make a decision. We should make this system better. That means compared with the control theory, we need the controller to make the system perform good. So in L3, we call it Nexus. It actually provide a engine. Provide a intelligent decision-making engine. That means we know the knowledge of the world. We know all the data, and now we have to make a decision for this to do its job. Let me give you an example, such as so we have a vehicle. Still, we can use the picking up container case. That is, we should pick up a truck to have the container loading. Then, so firstly, which one should we pick up? Obviously, there could be some candidates, such as they are empty and they can be the candidates of the picking up truck. But which one is the best? So Nexus can solve this kind of problem. It will pick up a truck which is fit for the current RTG status, because we have already collected all the data from all the devices. That means we can coordinate all the devices in the same scheduling plan. So we consider the current truck status, we consider the current RTG status, we consider the current QC status. So we make the right decision by picking up a truck, which is arrived at the arrived at a yard where when the RTG has just finished the picking up process. So that's the purpose of a we could say it a perfect planning of the decision. So in L3, the Nexus can provide this kind of function that we consider all the situation now of all the devices and make the most correct decision. So in level four, we actually when we have the decision, we should have a layer that to actually execute the decision. So in level four, we call it kinetic. Obviously, it contains all the device that can execute all the commands. Westwell actually provides all the intelligent devices to execute all the tasks. We have the product of truck, and we also have other metrics such as we have the IGV, we have the tractors. So based on all the abilities of the autonomous driving, we could execute all the decisions automatically. And then I will give you an example of how a single or how a independent system can reach its limitation and how ReeWell can solve this problem. Well, FMS is actually our one of our product, which is called the fleet management system. In this figure, it shows that FMS actually holds a critical position in the port workflow. Uh, in the normal port operation, every port or every terminal has TOS, which is the terminal operating system. Try to assign all the tasks, assign the devices where to go, and controls all the operations uh, internally. Uh, Mainly, it contains three big parts of them, which is the wharf management system, the yard management system, and the fleet management system. So the wharf management system is controls the task for QC. The yard management system controls the task for the YC or the yard crane. And for the FMS, it's obviously it's controls the tasks for all the fleets, or we can say the horizontal transportation. And we could see in the figure that in the FMS we have four parts of them, which contains by the HD map, vehicle dispatching, global scheduling, and the interface parts. So we could see that the FMS is focused on the uh, on the fleet level, which will ignore or the other parts is not his responsibility. Uh, in FMS, a single vehicle could have a task for itself instead of considering all the QCs and the yard cranes. Despite the FMS, our FMS could could driven all the intelligent devices of the autonomous trucks, IGVs, the mini truck even, or the auto SCs. It's actually can make a limitation. That means in this figure we actually have different parts of them. After we deploy the FMS in the different level, it could see a significant increase of all the efficiency. So let me give you an example. On the top left, we could see in the path planning parts, before we deployed FMS in the terminal, uh, they use manual truck. They don't have any path planning. So if we begin to deploy more and more autonomous driving trucks into the port, we could see the efficiency has a significantly increase at the beginning. But after the fleet reach some kind of level, uh, the result could reach a limit. It cannot increase fast, or it cannot increase anymore. And this phenomenon happens in the other parts, such as we have the intersection management, we have task dispatch, we have the deadlock prevention. All the functions are provided by FMS, but they all have the same trend that at the beginning, when we introduce the FMS, it can solve some kind of it can have a good performance at the beginning, but after a while, it can reach limitation. So how do we solve that? How do we break the limitation of the WellFMS? So we introduce the ReeWell, which consider all the elements, and we call it the multi elements scheduling. In this slide, we actually give you a example of the ReeWell. So this video is a demo of the current no, why it might be some problems. But yes, yeah, this one looks like this video cannot play well, but I will give you some explanation of what it is. So in this video, we could say, or now it is a picture, we could see that we have labels that it controls every part of the of the terminal elements, which is we could see the traffic congestion, we could see the yard crane tasks, we could see the yard tasks itself. That means every equipment has its own task lists, and we will consider all the tasks in our Nexus engine when we make the decision. And this different colors line is actually performs the path of every vehicle, and uh, it also consider the task from the vehicle itself. And yes, in the following, oh, it plays now. So yes, this labels shows all the tasks, as I said, of all elements in the terminal, and it can show the energy, show the efficiency, it shows all the schedule for all devices. So let me replay it. So here we could say why we call it time slice based scheduling. That means after we consider all the data in the model, in the level 2 model, Hymala model, we actually build up a sandbox of the spatial and the time at the same time. That means every decision making is based on the understanding of spatial and time inside the Hymala model. So after considering all the aspects, we actually can give the schedule of all the devices. So obviously here we have the QCs we could see and the ATs, uh, and also YCs actually, but it doesn't show here. So in this label, we could see that every device has its task in the same scheduling plan, and we could see how long the task will be exists, and when is the uh, device is idle or busy. So this is the most value ReeWell can provide. That means we could build up a real world. We could simulate all the devices in the sandbox, and we could give a most optimistic decision considering all devices. So how ReeWell is working, how ReeWell can do it. Uh, so here is the detailed explanation of how ReeWell do that. Uh, ReeWell is actually try to understand the world. It's a AI based, AI driven situation awareness. So L1 Cactus and L2 Hymala actually build up a physical sandbox together where the data node can generate the data. As I said, in the control system, it is can be considered as the input of the control system. All the data node generate data such as the CAM, the ERP actually provide the order or some sensors, and then all data will be collected into the Cactus, which is considered as the input, and then all the data will be after collected, all the data will be into the Hymala model, which build up which provide a understanding of all the data and try to build up a physical sandbox, which I explained before. So with all the understanding of the word, then we have a Nexus, where is a dual engine and event-driven AI decision making. So in this engine, we actually has three levels of the understanding of the word. The first level is the task memory, which we could see the short memory. It's very short because it's based on the current workplace, such as we have the current task list. We have a current status, the traffic, the running status of a single vehicle or a single devices. So that provide a task memory of current device. And then it comes to the midterm memory, which considering the recent situation, it might be a specific time period, such as 1 hour, 2 hour, or several hours. So that means it can give some understanding of a operation in a specific time period, such as in the current hour, it has a traffic congestion or not, or where could be the traffic congestion happens. And then we also have a long-term memory, which is the operation knowledge. Obviously, when we try to do the intelligent operation, we have to have some prerequisition knowledge about the operation. Otherwise, the intelligent operation could over the limitation or can break some rules. So all the operation conditions or the operation rules should be written first and considered by Hymala as the basic rules. So we built up some the RAG knowledge base, and then everything every decision making by the NEXUS could not break the rules. So after we have all the knowledges, we try to make the decision, and we provide two engines to make the decision. So the first engine would be the MARL engine, which can be considered as multi-agent reinforcement learning engine. So this one is actually mainly focused on the device's behavior itself. That means that provide the path planning, or the a global path or local path, short path for every vehicles to execute, because it's multi-agent reinforcement learning. So it mainly focused on the agent itself. So every device can be considered as the agent, and this engine will provide the most fitable uh, action or decision to every device. The other one would be the OR engine. So OR is the abbreviation of Operation Research. It provides the traditional algorithm on the task assignment. Uh, Although we have already seen previously that uh, the task assignment problem is a MP hard problem. It's very hard to have a global optimal solution in the limited time. But our OR engine actually provide a comparatively, or it can provide a optimistic result based on the result from the MARL engine. So it cannot work independently. It actually work together and give a better answer than before. So after all the decision making process, we actually output a efficiency first, energy first, or balanced mode. It depends on the object function of the OR engine. After we actually currently ReeWell has already created a significant value. After we deployed the ReeWell in different sites all over the world, we these numbers are collected from our on-site project. Obviously, it reduce the waiting time by 10%, can reduce the cost by 20% per cycle, and it reduced the error rate of every device by 60%. But of course, this one is compared with a manual operated devices. So if we would like to reach this rate, we have to introduce our autonomous driving products as well. And it provides a flexible computing. It can reduce the carbon emission by 10% on average. And of course, it can reduce the training time by 90%. Because for now, the operation form has been changed from the manually to the intelligent operation. That's the our willing to do after we deploy the ReeWell. And this is today's share. Thank you very much. I will give the host.